Hydrostatic pressure is the force that a fluid exerts, while at equilibrium, at a given point within the fluid. Over a given area, these forces can be added together to equal a resultant hydrostatic force. The line of action of the resultant force acts in compression and is always normal to the surface. It acts at the center of pressure, denoted by Cp, rather than at the center of gravity, denoted by Cg.
In this demonstration, you can see that the water comes out of the holes at different forces. These forces are caused by differences in hydrostatic pressure. The different fluid depths yield different hydrostatic pressures at each of the points on the bottle. At the top of the bottle, the water is coming out in a short stream, while at the bottom of the bottle, the water is coming out in a faster and longer stream. So why is the force of the water streams changing as we go down the bottle?
Let's derive the resultant force and the center of pressure in a hydrostatic situation. As you can see here, a submerged wall experiences a linear pressure gradient from point A to point B along its submerged surface. This pressure gradient creates a resultant force, Fr, whose line of action is somewhere below the center of gravity. We call this point the center of pressure, or Cp. We know that pressure is equal to force divided by area. Therefore, force must be equal to a collection of pressures over a given surface area. In our situation, this means that the resultant force is equal to the integral from A to B of negative rho g w h dh, where rho is the density, g is gravity, w is the width of the wall into the page, and h is the height of the wall. In the end, this simplifies to our resultant force being equal to rho g h squared w over 2, when we make A 0 and B h, the height of the submerged surface. The resultant force is at something called the center of pressure, which is somewhere below the center of gravity. We'll call the distance down to this center of pressure h prime. We know that this value h prime must be equal to h, the distance down to the center of gravity, which in this case is half the depth of our submerged wall, plus some delta y. From our notes, we gather that delta y is equal to the density times the gravity times the second moment divided by the resultant force. In this case, the second moment is equal to the width of the wall times the depth of the submerged surface cubed divided by 12. The resultant force is what we just derived, rho g d squared w divided by 2. As we plug in all of these values into the equation for h prime, we see that many things cancel out. In the end, we are left with h prime being equal to d over 2, our value for h, plus d over 6, our delta y. Fully simplified, this becomes 2d over 3. This is our center of pressure.
We've already seen a quick preview of this example, but now that we understand the key equations and principles behind hydrostatic pressure and resultant forces, let's revisit it. Here I have a plastic water bottle filled with water. Underneath each piece of tape is a small hole where water can escape the bottle. Let's see what happens when I remove the tape. When looking at the streams coming out of the bottle, it's apparent that as we move down the bottle, the stream is stronger. But how does that relate to our equations that we looked at earlier? This is due to the increase in pressure as the height of the fluid above the hole is increased. The previous derivations prove this idea since it demonstrates how the pressure at a certain point inside of the liquid is related to the height difference between the chosen point and the water line. Building on top of that is the relation between force and pressure. Since force and pressure are directly related, and in our demonstration the area stays constant, the force at the bottom is greatest for the stream of water coming out of the bottle.
As an overview explanation, hydrostatic pressure is the result of all the weight of the fluid on top of a given point in space. So in our example, the hole that is closer to the top of the water line has less water above it than the lower water holes. Thus, the closer the hole is to the water line, or the smaller h is in our equations, the less volume of water sits atop it, and the lower the hydrostatic pressure. Further, As seen in our initial demonstration, you probably noticed that the top water stream actually stopped. This was due to the hydrostatic pressure becoming too small to overcome the cohesive and adhesive forces.
Hydrostatic pressure and its resultant forces have many real-world applications. For example, large bodies of water, such as those in aquariums, exert a great amount of pressure on the structures that retain them. Engineers must consider the effect of such forces when designing retaining walls. Dams are barriers used to form reservoirs and are subject to an immense amount of hydrostatic pressure. Oftentimes, water is intentionally released from a reservoir. The release of pressure results in high-velocity flow, whose energy can be harnessed as hydroelectric power. Another example of hydrostatic pressure can be seen off-land, in our oceans. Hydrostatic pressure is a function of height. Pressure increases as depth increases. In fact, the ocean's pressure increases about 1 atmosphere for every 10 meters of water depth. Water wheels use a similar concept. Running water pushes against the paddles of the wheel, creating a force which rotates it. An axle, connected to the wheel, turns and drives belts or other machinery to create usable power. Lastly, hydrostatic pressure is important in designing water tanks and water towers. Like dams, the water within water storage containers creates pressure on the walls of the structure. The walls must be sturdy enough to withstand this pressure. Luckily, this force assists in pushing the water out of the storage tank and distributing it to its intended destination.